Module 1.3 will cover the Intergovernmental Panel on Climate Change, or IPCC, and projecting climate impacts into the future. The Intergovernmental Panel on Climate Change, or IPCC, is an international body that provides assessments of the scientific basis of climate change, its impacts and future risk, and options for adaptation and mitigation. The IPCC was founded in 1988 by the World Meteorological Organization and the United Nations Environment Programme. The objective of the IPCC is to provide governments at all levels with scientific information that they can use to develop climate policies and make important decisions. Every 5 to 7 years, the IPCC produces a set of assessment reports detailing the most recent climate change findings from leading scientists around the world. The reports are critical to informing decision makers about what scientists know about climate change so that they can make climate-informed policy decisions. The most recent set of reports that were published by the IPCC were related to the 6th Assessment Report, also known as the AR6. The 6th Assessment Report, released in 2023, states with high confidence that human activities, primarily through GHG emissions, have caused global warming, with global surface temperature reaching 1.1 degrees Celsius above 1850 to 1900 average. Widespread and rapid changes in atmosphere, ocean, cryosphere, and biosphere have occurred, and in the future, continued greenhouse gas emissions will lead to increasing global warming, with the best estimate of reaching 1.5 degrees Celsius in the near term in considered pathways and modeling. How do we measure that the climate is changing, and how can we project what will happen in the future? Scientists use something called climate models. Climate models are very complex computer programs that simulate the Earth's climate over a period of time. Climate models use equations to represent climate processes and interactions between the atmosphere, oceans, land surface, and ice sheets. Climate models can be global or zoom in on a specific region to provide finer resolution and more accurate simulations. Scientists input data into the model related to climate components and other factors such as greenhouse gas emissions, and the model will simulate various processes of the Earth's climate under this particular scenario. Scientists can use climate models to explore different scenarios by changing the input information. So we can input different greenhouse gas emission scenarios into the climate models to explore how emissions may change the climate in the future. Let's explore this further. Emissions scenarios are a way to help us understand what the future could look like so that we can create climate policies and plan for the impacts we may experience. Often the scenarios consider many factors, such as our future greenhouse gas emissions and climate policies, deforestation, economic activity, population growth, technology, and more. By looking at different scenarios of the future, we consider a range of possible futures that could occur and plan accordingly. Let's look at some examples. A common way to represent different scenarios is through representative concentration pathways, or RCPs. The RCPs are labeled after a possible range of radiative forcing in the year 2100. When we say radiative forcing, we mean the energy change or imbalance in the atmosphere caused by greenhouse gas emissions. So the more emissions, the more energy imbalance, meaning a higher radiative forcing. This graph is showing the change in global average temperature from 1900 to 2100 for 3 different RCP scenarios represented by the colored lines and shadows. 29 climate models were used to generate this graph, and the shadows are representing the range of model projections for each RCP. Each model generates a slightly different projection based on the data that has been input, and so we combine all of these outputs to show the range of what the future could look like. Let's look at these 3 commonly used RCPs and see what they mean. RCP 2.6 is the blue line and shadow. RCP 2.6 is a low emission global scenario. In this scenario, it requires strong mitigation actions where emissions start to decline by 2020 and reach zero by 2100. This scenario indicates global average warming levels of 0.9 to 2.3 degrees Celsius by 2090. RCP 4.5 is the orange line and shadow and represents a moderate or medium global emission scenario. In this scenario, measures to mitigate climate change occur and emissions peak around 2040 and then begin to decline. This scenario indicates global average warming levels of 1.7 to 3.2 degrees Celsius by 2090. So warming is a few degrees more than the 2.6 scenario, as you can see based on the difference here. Finally, RCP 8.5 is the red line in shadow and represents a high global emission scenario, where emissions continue to rise throughout the century. This is often known as the business as usual or the worst case scenario because there are no climate policies to mitigate our greenhouse gas emissions. In this scenario, global average warming levels are 3.2 to 5.4 degrees Celsius by 2090, and you can see how big the difference in global average temperature is for RCP 8.5 compared to the moderate and low global emission scenario. In addition to temperature, we can also use emission scenarios and RCPs for other climate variables. This graph shows the change in average precipitation from the average in 1986 to 2005 to the average in 2081 to 2100. The Earth on the left is showing the change in average for RCP 2.6. Recall this is the low emission scenario. And the Earth on the right is showing the change in average precipitation for RCP 8.5, the high emission scenario. As you can see, we see a large change in precipitation for the high emission scenario compared to the low emission scenario. I encourage you to pause the video here if you want to explore these graphs further. More recently, scientists, researchers, practitioners, and decision makers have realized that determining how much the climate will change also depends on how society grows and develops. To represent these complex societal developments, shared socio-economic pathways, or SSPs, were created. These pathways make assumptions about how population, education, energy use, technology, climate change mitigation, and more may change over time. There are 5 families of SSP-based scenarios. In this figure, the scenarios are broken down along the axis of increasing challenges to mitigation on the y-axis and increasing challenges to adaptation on the x-axis. Let's look further at some of these SSPs. SSP1 in the lower quadrant here is categorized by low challenges to mitigation and low challenges to adaptation. This is known as the sustainability scenario. As you can see in SSP1, policy is focused on sustainable development. There's international cooperation, reduced inequality within and across countries, low consumption, and low population growth. Let's move across here to SSP3, which is the regional rivalry scenario. It's categorized by high challenges to mitigation and high challenges to adaptation. We can see policy is focused on security. There are barriers to international trade and high inequality. There's slow economic growth, low population growth in rich countries, but high population growth in other countries. If we move down below SSP3, we can see SSP4, which is categorized by high challenges to adaptation, but low challenges to mitigation. This is known as the inequality scenario or a road divided. So policy is focused on elite. There's high consumption and high inequality. There's low to medium economic growth, low population growth in rich countries, high in other countries. If we move across the quadrants here to SSP5, this is categorized by high challenges to mitigation and low challenges to adaptation. This is known as the fossil fueled development scenario taking the highway. We can see policy is focused on free markets. There's high consumption, so high emissions. There is international cooperation and reduced inequality, but there's high economic growth and low population growth. And then the last SSP, as you can see here, is SSP2. It's kind of the middle of the road. So there's moderate challenges to adaptation and moderate challenges with mitigation. And it says continue with current development patterns. So we've talked about SSPs, or shared socioeconomic pathways, which represent different social and economic development patterns. But how are SSPs different than RCPs, which we talked about a few slides ago? SSPs further refine the RCPs by providing more standardized and specific future trajectories related to the different social and economic development patterns that we looked at on the last slide. The SSPs help determine which RCP is used. This information is then input into climate models to produce a range of climate projections and a range of possible futures. In practice, SSPs are labeled using this format, where the SSP represents the social and economic growth pathway, and the number after represents the radiative forcing, as we discussed on the RCP slide. So for example, SSP2 4.5 represents the middle of the road SSP scenario and a medium emissions scenario where emissions begin declining in 2050 but don't reach zero by 2100. Another example which is commonly used is SSP5 8.5, where again the SSP5 represents the fossil fuel development SSP scenario, and the 8.5 represents a very high emission scenario where emissions continue to increase and triple by 2075. The SSPs were used in the most recent assessment by the IPCC, the AR6, and are now becoming the standard way to project future climate. We will see the SSPs again when we look at how the climate is changing in Suriname. When considering future climate change projections, there are several sources of inherent uncertainty because we can't predict with 100% certainty what will happen in the future. Let's explore these three areas of uncertainty. So the first is natural variability of the climate system. Natural variability through phenomena such as El Niño Southern Oscillation, or ENSO, are internal to the climate system and are not captured well in climate models. Other sources of unpredictable natural variability are volcanic eruptions or solar output, and these are difficult to represent in models of the future climate system. Due to natural variability, one way to mitigate this uncertainty is to use longer-term averages, so 30+ years, which are more reliable than estimating conditions for a single year or for a shorter-term average. Another source of uncertainty is within the climate models themselves. Climate models follow the laws of physics and are mathematical representations of a future climate system, meaning naturally climate models are different than reality. Each climate model is unique and may have different levels of simplification, different grid size, different ways to represent complex phenomena such as clouds or vegetation cover. Consequently, each model may produce a slightly different projection despite using the same greenhouse gas emission scenario. A way to mitigate this uncertainty is to use an ensemble or many climate models to reveal the range of possible futures and to show where climate models show agreement. This is not a consensus, but a best estimate, as there is a wide range of possible model outcomes. Finally, the last area of uncertainty is with the future greenhouse gas emission scenarios, because it's difficult to predict exactly what global emissions will be in the future. To provide the best estimate of future emissions, climate models are run with different emission scenarios, RCPs and SSPs, as we talked about. to show the range of possible futures. Despite this uncertainty, we must use the best available science and knowledge and act accordingly. 2100 is still somewhat far away. We have the power to decide which path we follow now. All paths will lead to climate impacts that are more extreme than what we currently face, but the severity and frequency of those impacts depends on the amount of greenhouse gases we emit. The low emissions pathway, here in green, where we keep temperatures below 1.5 degrees increase, will lead us to only slightly more extreme climate impacts. Whereas the high emissions pathway, here in red, which takes us to 4.5 degrees increase, will lead us to more frequent, intense, and extreme climate impacts. The more we emit, the more likely we will follow the high emissions pathway that leads us to 4.5 degrees increase and more frequent, intense, and extreme impacts. In other words, how we behave now when it comes to greenhouse gas emissions influences which path we will follow and how extreme the climate impacts will be in the future. I find it helpful to think about this like a trip to the dentist. Let's say you leave the dentist and you have 1 year before your next checkup. Based on your dental hygiene behavior, so how often you brush your teeth, how often you floss, what kind of toothbrush you have, if you use mouthwash, and if you eat lots of candy, this will determine what happens at your next checkup. So let's say you have really great dental hygiene when you leave your dentist appointment. This would put you on this green pathway and would lead to a minor cavity. Let's say, on the other hand, you have not so great dental hygiene. This would lead you on the red pathway, and you might have a really bad cavity and even a root canal. In other words, how we behave now influences how likely we are to get a bad cavity. The longer we wait to start good dental hygiene, the further along the red pathway we will be on our way to the root canal. Let's say we wait until a month before our checkup to start flossing and brushing our teeth. Our past behavior will already have committed us to the root canal / bad cavity outcome. As things currently stand, we are on the high emissions pathway, or the red pathway, headed towards the root canal and some seriously extreme climate impacts. But we have a choice on which path we will continue to follow. Before we wrap up this module, I want to highlight the concept of keeping temperatures below 1.5 degrees Celsius above pre-industrial temperatures. In 2018, the IPCC released a special report on the impacts of global warming of 1.5 degrees Celsius above pre-industrial levels. The report highlighted the importance of limiting global warming to 1.5 degrees because exceeding this limit would lead to more severe and irreversible impacts on ecosystems, human societies, including vulnerable communities, and the planet as a whole, through increased heat waves, more intense storms, sea level rise, and risks to food and water security. Keeping temperatures below 1.5 degrees Celsius would require rapid and substantial reductions in greenhouse gas emissions, aiming for a net zero emissions by 2050. Achieving this goal would require unprecedented changes in energy systems, land use, infrastructure, and societal behavior. To summarize, the IPCC is an important international organization dedicated to providing assessments of climate change science and impacts. We have tools such as climate models to help predict future climate. However, future climate depends on our greenhouse gas emissions and future economic and social development. We have the power now to choose which future we want and to keep temperatures below 1.5 degrees Celsius.